Hello everyone. In this lesson, we will study about some rearrangement, which are coming under nucleophilic aromatic substitution reaction. You know, a nucleophilic aromatic substitution is a substitution reaction in organic chemistry, in which the nucleophile displaces a good leaving group on an aromatic ring. In content we will discuss von Richter rearrangement, Sommerlet-Hauser rearrangement, and Smiles rearrangement along with its general scheme, reaction and mechanism. Von Richter rearrangement. Von Richter rearrangement is a name reaction in organic chemistry. It is named after Victor von Richter, who discovered this reaction in the year 1871. It is the reaction of aromatic nitro compound, which react with potassium cyanide in aqueous ethanol to give sinus substitutions by the carboxyl group. Sinus substitution means a type of substitution reaction in which the entering group takes a position on an atom adjacent to the leaving group. The reaction below shows the classic example of the conversion para-bromonitrobenzene into meta-bromobenzoic acid. When aromatic nitro compounds are treated with cyanide ion, nitro group is displaced, and a carboxyl group enters with sinus substitution. The new group is always ortho to the displaced group, it is never meta or para. This reaction is one type of nucleophilic aromatic substitution. So, besides the bromo derivative, chlorine and iodine substituted nitroarones, as well as more highly substituted derivatives, could also be used as a substrates in this reaction. This rearrangement can also be inhibited in presence of potassium ferrocyanide and sodium sulfite. This reaction gives best results when electron withdrawing groups are in ortho and para positions. However, yields are generally poor to moderate yields, ranging from 1% to 50%. Reaction mechanism of von Richter rearrangement. This reaction proceeds through a nucleophilic attack of cyanide ion, which is ortho to nitro group, followed by intramolecular rearrangement. First, the cyanide ion attacks the carbon atom in step 1, which is in ortho position to the nitro group. After this, the compound regains its aromaticity in step 2. In step 3, the negatively charged oxygen atom attack the neighboring carbon atom to form a 5-membered ring. In the next step, nitrogen accept 2 proton to form NH2, which undergo condensation reaction with nitro-SO compound, that means removal of water molecule, to form a double bond between the 2 nitrogen atoms. See the structure number 6. In step 5, the hydroxyl group attack the carbonyl carbon, and the bond between carbonyl group shift to oxygen atom, which makes the oxygen atom negative. In the next step, the elemental nitrogen leaves the system for the opening of the ring and form a carb anion. In the last step, the carb anion is protonate, and 3-halogen benzoic acid is formed. Now we'll discuss Sommerlet-Hauser rearrangement. The Sommerlet-Hauser rearrangement is a rearrangement reaction of benzyl quaternary ammonium salts. It is named after M. Sommerlet and Charles R. Hauser. When benzyl quaternary ammonium salt react with alkali metal amide, best example is sodomide, then it undergoes a rearrangement, to give benzylic tertiary amine, that is N,N-dialkylbenzylamine, having a new alkyl group, in the aromatic ortho position. For example, benzyl quaternary ammonium iodide, rearrange in the presence of sodium amide, to give ortho-methyl derivative of N,N-dimethylbenzylamine. Since the product is a benzylic tertiary amine, it can be further alkylated, and the product, again, subjected to the rearrangement. This process can be continued around the ring until an ortho position is blocked. This rearrangement reaction occurs with high yield. The Sommerlet-Hauser reaction highly favors two conditions. One is in presence of polar solvents like NH3, DMSO, and HMPA. Second one is low temperature conditions, which also favor the reaction. Reaction mechanism of Sommerlet-Hauser rearrangement. The reaction proceeds with deprotonation of the benzylic methylene proton. Deprotonation means removal of protons. Though this benzylic hydrogen is most acidic, it loses a proton, which is taken by the NH2- nucleophile of sodomide, to give the ylide, denoted by number 1 in mechanism. The first ylide formed is in equilibrium with the second ylide, which is denoted by number 2. Second ylide is formed by deprotonation of one of the ammonium methyl groups of first ylide. Then the second ylide undergoes a 2,3 sigmatropic rearrangement and subsequent aromatization to form the final product, that is, N,N-dialkylbenzylamine. Last rearrangement S, Smiles rearrangement. The Smiles rearrangement involves the intramolecular nucleophilic aromatic substitution reaction. It is named after Smiles, who discovered this reaction in the year 1894. It involves attacking on aromatic system, which possesses electron withdrawing group at ortho or para position, to the reaction center, connected to heteroatoms. In this reaction, W denotes the electron withdrawing group, which may be NO2, SO2, chlorine etc. Here X, in the arene compound, can be a sulfone, a sulfide, an ether, or any substituent, which is capable of dislodging from the arene, carrying a negative charge. The terminal functional group, in the chain end, that is Y, is able to act as a strong nucleophile. Generally these are the conjugate base. For example, an alcohol, amine, or thiol etc. Here arene, which is the reactant, gets activated by the presence of an electron withdrawing group, if it is present in the aromatic ortho position. For example, chloro, an alkoxide, can accelerate this rearrangement. The solvent, such as THF, has been found to give positive effect and increase the rate of the Smiles rearrangement. Now we'll see the reaction mechanism of Smiles rearrangement. In this mechanism, the end group of amine, in structure 1, after losing proton, by base OH-, acts as a nucleophile. In step 2, the nucleophile attacks the carbon of benzene ring, to form a carbonium. Then in step 3, the bond between carbon and ether oxygen break, which makes the oxygen negative. In the last step, negative charged oxygen atom, then abstract a proton from water molecule, to form the product. Thank you.